So this is basically what I did with that Year 10 cohort. If you're wondering how they got to that stage in 5 weeks, I'm going to whiz through this because you guys should understand it very quickly. So this is actually ancient Mayan. The ancient Mayans actually came up with the concept of zero roughly the same time as the Hindus, but it's forgotten about for some reason. But their concept of zero, it was called Mixbal, and they thought of zero not as nothingness, but actually as the seed of all other numbers, and that's what Mixbal apparently means in ancient Mayan, but I don't know whether anyone speaks ancient Mayan here. So these were the symbols. Obviously, it's vigesimal, which is base 20. They needed 20 symbols. And you'll probably recognise these. They're pretty obvious. Obviously, they didn't have matchsticks in those days. I think they were just sticks and beans and a shell. After 9, we moved on to 10, which is 2 sticks, and so on, and so on, 2 sticks and 4 beans, up to 19. And of course, 0 to 19 is 20 symbols, so now we've run out of symbols. So how do they represent 20? Anyone? Like that. Okay, so they had a 1 in the 20s column, but it wasn't a column, it was a row or a box, and they had 0 in the units. And then they started again. So, what's this number? Okay, it's, yeah, you're right. I would probably call it 60-10. Yeah, 3 20s, 60 and 10 units. Now, obviously that's 70 in base 10. They probably, I don't know, typically in bases you'd call it, you know, or 3 to 10 or something. Yeah. Cool, so there we go. Oh, what about that one? Yeah, good. I heard a couple of things. By the way, you know, I'm saying, what about that one? I'm looking at you all, and this is how your students feel. You're in a classroom full of maths teachers, and can you imagine anything more embarrassing than getting the answer wrong? So yeah, this is 5 20s, which is 117, so 117. What was interesting about this was that it was almost like, what do you call it, experimental archaeology, that one of the kids said, oh, well, every stick in that box means 100. And I hadn't really thought about that, and that's absolutely right. And maybe that's what they thought. Every stick in that box is 100 rather than 5 20s. So that's pretty cool, isn't it? We might have rediscovered how the ancient Mayans thought about number. Okay, what about this one? Anyone? In your head? Okay. You want to say, go on, give us it. Yeah. That's 100. That's 1 in the, what did you say? 400s column, yeah, because it's 20 squared, and 5 in the 8000s column. So yeah, well done. So that's 5 8000s, 1 400, 5 20s, and 11 units. Otherwise, I mean, you know, you could do that in your head, I suppose. 40,511. Cool. It's Sunday, so. How about that? That's quite a profound question. Anyone who really understands number bases should have their arm straight up in the air. Brilliant, well done. 19 and 19. Can you explain why?
Well, I just did it as 1 minus 400 minus 1.
Which is absolutely brilliant mathematical elegance. It's 1 less than 400. Because you that's how you do it. It's got to be 1 less than 400, so it's 1 less than 100. So these 2 columns or rows or whatever have to be full. In the same way as 99, 9 is the maximum symbol in base 10. So that's 1 less than 400, and you can just verify it. Yes, it's 399. A friend of mine, David Horton, who some of you know, had a lovely way of thinking about that, which, in fact, I'll just show you this one. So what do you think this number is? Brilliant. And isn't that wonderful? Someone just goes, oh, it's 7,999. It's like, whoa! Are you a computing genius? No, it's one less than 8,000. It's 1990. Did I do something wrong? Oh. Oops. Okay. I thought I was well prepared for this, but it turns out I'm not. So, that's all right. So anyway, David Horton, he gave this analogy. He said it's like one of those mechanical counters that you click, 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 and the wheel turns for each number, and it turns in the unit column, and then there's a little pin connected so that when it gets up to 9, it flips over the next column along, and you get one of the tens increasing, and then when it gets to 99, the 2 pins flip over, and then one in the hundreds. And this is the same, but with 19 digits on each wheel, which is quite a nice way of thinking about it. And then after we'd done ancient Mayan, they were pretty proud of themselves because they could actually count in ancient Mayan. And I said, you do realise that's completely and utterly useless in life, because all the Mayans died out long ago, and they were so thrilled. So they'd learned something really academic and useless. So base 10, I mean, I'm not going to go through this, you should understand it quite well by now. That's what base 10 looks like. But and then other number bases. So base 7, we've got 7 symbols, 0 to 6. How do you represent 7? What do you think? 1, 0, good. And of course they say 10 a lot. And you have to say, no, it isn't 10, it's 7. That is 7, 1, 7, not 1, 10. So it's 1, 0. That's a better way of saying it. And then this is the counting in base 7, up to 6, it's same as base 10. Then it goes 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 2, 0, 2, 1, 2, 2, 2, 3, and so on, until you get to, 3, 6 is 27, because it's 3 sevens, which is 21 and 6 units, 27. You see what this is doing in a way? This is actually giving a really profound understanding of place position, rather than just a superficial one in base 10. It's also introducing indices and 7 to the power 0, and anything to the power 0. And if you really want, you can go this way and go 7 to the power minus 1. What does that mean? And it's a 7th, and 7 to the power minus 2, 49. That can be done really at year 8 level, if they understand this. So here's base 3. It just has 3 digits, 3 symbols. So 1, 0 now means 3. And base 3 counting looks like this. I'm going quickly because I'm aware of the fact, otherwise I want to get to the end of my show, and I'm sort of absolutely bang on at the moment. So, look, 1,000. No, it isn't. It's 127. It's 1 in the 27th column. So 222 is the equivalent of 999 in base 10. 222 is 2 in the 9s column, 3 squareds column, 2 in the 3s column, and 2 in the units column, so that it's 18 plus 6 plus 1, so that gives you 20, plus 2, sorry, that gives you 26. I'm going quickly, but you have got the notes. So base 2, so that was base 3 columns. Base 2. And how useful is base 2? I mean, the answer is very, because we all use it in computers and everything, but not many people actually understand what bit and byte and 16-bit, 32-bit and 64-bit mean, or why 32-bit operating systems can't address more than 4 gig of RAM or stuff like that. But actually, it's very easy to explain if you understand base 2. So base 2, oops, doesn't look like that. That's a student looking at a treat. Base 2 looks like that. Now, 2 to the power 8 is 256, which is a sort of number that you kind of know. 1 byte is actually 8 bits, so each one of these is called a bit, binary digit bit, and it just is on or off, 1 or 0, 5 volts or 0 in electronics. Or in CMOS it's 15 volts and minus 15 volts or something like that. So that if you put these switches together, if you put 8 of them together, you can represent up to 255. If all of these were 1s, it would be 1 less than 256. So 0 to 255, so you can represent 2 to the 8 or 256 different states. And that's how computers encode writing. If you type a letter on the keyboard, every letter you type, or space, or funny character, that gets encoded with something called ASCII code, which is a lookup table of values. So, for example, little a, I think is, I can't remember, 96 or something. It's actually a 11110000, whatever that is, 64 plus 32. Yeah, 96. And so you just have a lookup table. So you can represent a letter, a character, with 1 byte. And if you want to know how many bytes you need, not using Microsoft Word, but using just a text thing, you just need to multiply the number of characters by, well, that's how many bytes you need for storage. And then 32-bit operating system has 32-bit words. So it can represent numbers up to, I don't know, 16-bit is 65,536, which is 2 to the power 16. 2 to the power 32 is something like 4 billion. Yeah, 4 gig. And that's why you can't address more than that in a 32-bit operating system. Interesting, huh?